So what I'd like to do now is, with number 29 on this page, is just set up the integrals, because you guys can do the integrals once they're set up. So, and you referring to this sheet as necessary for this problem, where we have actually 4 different axes that we're going to do. So our first one, we're take them one at a time. Part A for this problem is rotated about the x-axis. So if I rotate this about the x-axis, right, that's there. So, you know, think about what kind of shape results. That's really where you got to start. You got to think about what is the shape going to look like. So if you know, first create a reflection. A lot of you guys can do it just from, okay, I get it from the cross section. This is a cross section, and you know, you could probably figure out, you know, everything you need from there. But you know, generally what this looks like is the outside's going to be a cylinder, and the inside's going to be sort of a cup. So it's like a really thick glass, you know, when it's like heavy on the bottom, and there's a lot of glass on the bottom, and it's only got a little bit scooped out. But you could drink from that glass. All right. So how are we going to set up the integral? So this shape is around the x-axis, and it's compound. It's made up of 2 functions. So we have an outer function, which is this one up here, y equals 2, and an inner function, which is this one in here, which is y equals square root x. Right, because that's our given functions. So I'm looking at a shape that has a hole in it. It's compound, so I'm looking at this. I'm going to do top minus bottom. Although, by the way, you could always use outer minus inner. That will always work. Okay, so I'm going to use this formula. So I'm going to write that the volume is equal to pi times the integral from. Now, I'm also going to think about, this is x-axis. So, you know, on one of these, so my limits are x coordinates that I'm integrating with respect to x. And my equations need to be solved for y, which makes sense with the y equals 2 and y equals square root x. All right, so these are going to be x coordinates here, 0 to 4, because my x coordinate is 4. All right, and then I have to do g of x squared. So my outer function is just 2 squared, minus my inner function squared, which is square root x squared, and then dx. And then you would just do that integral. Not too hard to do. Not any symmetry that you can take advantage of there, but that's an easy one to do. All right, let's look at what they want us to do in part B of this problem. They want us to rotate about y-axis. So rotate about y-axis. All right, so I have the same shape, looking like this. Here's the point 242 again, 42 right there. Here's our y equals 2. Now I'm going to rotate about the y-axis. Okay. So, you know, let's make a reflection about the y-axis. At the very least, you know, right, draw the reflection. When you're doing these, at least draw the reflection. All right, and then if you want, try and fill in the 3D aspects of this. This is a funnel. It's a tornado. It's flat on the top. It's funnel-y on the side. Yeah, there you go. Okay, so, all right, so this is not a compound shape. This does not have a hole in it. It's solid, because the axis you're rotating on is actually a boundary of the shape. So it's a simple shape. It's rotated in the y direction. So this is what I have. I have a simple shape rotated about y-axis. So this is my formula. Very simple one. V equals pi integral. Now the a and b, now I'm on this side of the sheet, right? So my limits are y coordinates. That's what we got to watch for. Am I using y or x? This is 0 to 2. All right, and then I'm doing f of y dy. Oh, my equations have to be solved for x, and they're not. My equations are not solved for x. So my y equals square root x. I need to solve that to be x equals y squared. And then my other equation, I don't have another equation. The other equation, if you want, is x equals 0. But I don't have another equation. That's just it, right? Because I'm here. There's only one function. All right, so that's what it is. It's y squared. So integral 0 to 2, y squared squared dy. And that's that one. All right? Then B, C. C comes after B. After B comes C. Part C of this problem wants you to rotate about the line y equals 2. All right, so let's sketch our shape again. It goes up to the point 4, 2. All right, and it's got this boundary and this boundary. The y equals 2 line. All right, now we're actually rotating it around the axis y equals 2. So the axis we're rotating it around is one of the boundaries of the shape. That's what makes it simple, by the way. So what makes it not have a hole in it is the axis around which you are rotating the shape is a boundary of the shape. All right, so there's our reflection. This one's going to be, it's also sort of funnely, but it's a funnel on its side this time. It's also solid like the last one. All right, but so this is a simple, but it's off axis. All right, it's off the axis. It's rotated around y equals 2. So it's simple, it's off axis. Let's find that. Here we go. Somewhere. Oh yeah, here's a simple shape around the y, all right, revolved around the line. Oh, this is around y equals k. Y equals k. So we're here. So it's not y-axis. It's really more like an x-axis rotation because we're going around y equals k. All right, so this is what we're going to do. We want our equation solved for x. We want dx, and we want f of x minus k. All right, so we're going to do the integral. So since we're integrating with respect to x, we're on this side of the sheet. Our limits are x coordinates. So we're going from 0 to 4, the x coordinate, 0 to 4. All right, and I have to do f of x minus k in parentheses squared. So my f of x, let's remember it was y equals square root x. So square root x minus my k is 2 squared dx. Boom. And do that integral. It's a little harder because you just square this out and you're going to have a 2 square root x term. And then, you'll have to use power rule. You get x to the 3 halves, 2/3 x to the 3 halves times 2. You can do it, though. So there's that one. All right, part D. Part D says revolve it around the line. Oh, let me label this up a little bit. This is the line y equals 2. So next time we're going to rotate. Let's go ahead and put the full words, rotate about. Okay, this one we're going to go rotate about x equals 4. So same shape once again. Let's have this shape. All right, but we're rotating it about the line x equals 4. Now this is the 0.24 right here. So we're rotating about this line right here, x equals 4. So when we rotate it, we're going to have one of those, sort of like a thick-bottomed glass again. But this time it's going to be facing down instead of facing up. Right, there you go. There's the shape. The outside is going to be cylindry. Outside is cylindry. Inside it's got a bowl cut out. So if that helps at all, I don't know. But so now you can see this is a compound shape this time. There's an inside and outside function. This shape has a hole in it. All right. Also, you can think the axis about which I'm rotating it is not a bound of the region. So the axis about which we're rotating the region is not a boundary of the region. Therefore, we're looking at a compound shape. Looking at a compound shape, it has a hole, but it's not about the x-axis or the y-axis. It's an off-axis. We're doing, in fact, the line x equals k. So that's going to be this one. So I need my equations solved for x. So I need to have my equations as my inner equation. Let's go ahead and label my inner equation. This is my inner equation. And since I need it solved for x, it's going to be x equals y squared. Is that what it is? I'm lost. Yes, it's x equals y squared because it was y equals square root x. Okay, now where's the outer function? The outer function is here. All right, and that was actually given in the problem as part of the boundary. Is part of the boundary of the shape was, find it. Oh, I know. This is so subtle now. So if I look at it over here, the inner shape is x equals y squared, and the outer function is x equals 0. And that's the one that was given to you. But by the way, when you rotate it around here, you get x equals 8. So which one are we going to use for the outer function? X equals 8 or x equals 0? So the cool thing is, it doesn't matter. I could use this x equals 8 because it's, 0, 4, 8. Use x equals 8 or use x equals 0. I'm going to have the same thing. I'll show you what I mean. I'm going to set it up with x equals 0 because that was given as a boundary of the problem. All right. So then I would have my volume is equal to pi times the integral. Now this is we're rotating about x equals 4, so we're on this side, so we're using the limits are y coordinates. So my y coordinates go 0 to 2. So you got to really watch what the limits are. All right, and then I got to go outer function. So it's outer function minus k, then inner function minus k, right? Outer minus inner. Okay, so the outer function, I'm going to write it as 0 minus my k, which is 4 squared, right? K is just the axis you're revolving around, minus my inner function, which is y squared, also minus 4 squared dy. All right, so that's following this format right here. You have it right there. Okay, now look, what if I use the outer function as x equals 8 instead of x equals 0? Would it change the problem? 0 minus 4 is negative 4, squared is 16. 8 minus 4 is 4, squared is 16. It doesn't matter, which makes sense because it's the outer function no matter which one you use. All right, and this is you do that integral. So there you go. That is off-axis revolutions. So next up, volumes of known cross-section. So by the way, these are all in volume practice number 3, which is posted. It's part of the homework. And so you can, work on volume practice number 3. It's got off-axis x and y, some tricks, I think, tricksy things in there. And then, then volume number 4 is going to be the known cross-section, which we must do next.